Good morning everybody. Let us start our last lecture on design of steel structures. आज की क्लास में हम देखो क्या करने वाले हैं बेसिकली compression member as well as beams हम आज की क्लास में कंप्लीट करेंगे. So in the last lecture we have basically talked about mostly talked about tension member है ना, याद होगा आप लोग को. लास्ट क्लास में हमने टेंशन मेंबर के ऊपर खूब सारी बातचीत की थी. आज की क्लास में we would be mostly talking about compression member as well as the beams. आज की क्लास में हम लोग compression member as well as beams के ऊपर बातचीत कर लेंगे. ठीक है, इतने इंपॉर्टेंट टॉपिक्स नहीं है, कम ही क्वेश्चन आए हैं आपके एग्जाम में, सो डोंट वरी अ लॉट. बहुत बेसिक क्वेश्चन पूछे गए हैं. compression member as well as beam, इन्हीं के ऊपर आज बात करेंगे. compression member क्या है, चलो देखते हैं हम लोग. लेट्स सी. चलिए लेट्स स्टार्ट द क्लास. Let's begin with it. What is a compression member? Let us see. So structure which carries axial compression is known as a compression member. Various types of compression members are there. We can have a stanchion, like in the steel structure the main compression member is known as a column, whereas in the steel structure the main compression member, that is a large section carrying the axial compression, is known as a stanchion. The stanchion is a vertical compression member in a steel building, main compression member. Then we have a strut. These are used in trusses. In the trusses and in the bracing the compression member is known as strut, whereas tension member was known as tie. Then in the crane the principal compression member is known as a boom. Okay. Now compression member may fail by various types. First type is squashing, like crushing. Squashing is analogous to crushing in RCC, that is reinforced cement concrete column. So in the squashing what happens? It happens in a very short column. So when the steel reaches its yield value, it will yield, obviously it will lead to squashing here. Then we have local buckling, flexural buckling, torsional buckling and flexural torsional buckling. So this is first kind of failure, that is squashing. So squash load is nothing but Fy by gamma mo into gross area of the cross section. So here local buckling will not occur. What happens in local buckling? You can see here that the column fails locally, either the flanges fails or the web fails, but the overall failure of the column have not taken place. It happens generally in thin sections. Okay. Then we have flexural buckling, that you have seen. See, this is my flexural buckling, that is in the column bends about the minor principal axis. And then we have the torsional buckling, that happens in when we try to twist a column. Then we have a combination of two, that is the flexural torsional buckling, that happens generally in the case of unsymmetrical section, like single angle with one leg with load applied through one leg. In that case you can have a flexural torsional buckling like this. Clear? So this is my flexural torsional buckling, but this is not in your course, so we would not be discussing it. Now effective length of the column is defined as what? That is K into L, where K is the effective length factor. Theoretically, if you will see, when both the ends are fixed, effective length factor theoretically is taken as 0.5 K, but as per IS code K will be taken as 0.65. When one end is fixed, one end is fixed and one end is hinged. In that case the theoretical value of K is 0.7, but recommended is 0.8. One end is fixed and one end is free, means it can only move in the x direction, but rotation is restrained. Only rotation is restrained here, like a slider support you might have seen. K is taken as 1, theoretically, but as per IS code it will be taken as 1.2. Both ends are hinged. In that case, K is 1 in both the cases. One end is fixed and one end is, you can see one end is free. It's free end, so 2 both the ends. One end is hinged and one end is having a slider support again, so 2. Got my point? Here you can see that in these cases the IS code have increased the K values. Why? To account for, see here we are saying that there is a complete fixity at support, but in reality complete fixity cannot be ensured. So, to account for this, K has been increased by IS code, lack of fixity. Okay. These all things I have written. So, tendency of a member depends upon its slenderness ratio. Now, lambda, that is the slenderness ratio, is defined as what? That is LE by R minimum. LE is the effective length. Lambda is what? LE by R minimum. This is my lambda, that is LE by R minimum. So, the tendency to bends depend upon lambda. Axis about which my lambda is maximum will be my axis about which the buckling will be taking place. So, this is a slenderness ratio. Okay. Now, axis of symmetry or an axis perpendicular to it are the principal axis. Here, like in the case of I section, this is the principal axis, YY, ZZ, where ZZ is the major principal axis, YY is the minor principal axis. This you all know. Angle section, UU is the major principal axis, VV is the minor principal axis. Okay. So, the stance ratio, there is a maximum limit of stance ratio to account for any accidental loads or construction loads, and to take care of any probability of members being subjected to unexpected vibration. So, member carrying compressive load resulting from dead and live load, lambda max can be 180. You cannot exceed lambda max beyond this. A tension member in which we have reversal of direct loads, this we have already seen, again lambda max is 180. A compression member in which the compressive load is due to wind or earthquake, less critical. So, here lambda max is taken as 250, and a tension member in which compression load is due to wind or earthquake, 350. Compression flange of a beam, 300. Very important table, please remember this directly. Many times objective questions are asked from this part only. Okay. So, to account for local buckling, my code have specified 4 classes of section, that is class 1, 2, 3, 4. Class 1 is a plastic section, class 2 is compact, class 3 is semi-compact, and class 4 is slender. So, plastic section is the one in which the plastic hinge can also form and the collapse mechanism can also occur before local buckling. That is the best section, that is a plastic section, means it have the full rotational capacity as well as the plastic hinge can also develop. In class 2, that is compact section, plastic hinge can form, but before attaining the rotation required for formation of collapse mechanism, local buckling will occur. Semi-compact section, in which in this the only external fibers yields, beyond that local buckling will occur. Slender section, in this case my outer fiber will also not yield, worst of all the sections. Okay. Before yielding of the outer fiber, the local buckling occurs. Now, whether the section will be plastic, compact or semi-compact, that will depend upon width to thickness ratio. Code have given this table, but not important. Let us proceed further. Now, let us see beyond this. You can just go through it if you want to. Effective sectional area is summation of B into T. See, in the case of compression member, the total area is taken as effective only if the member is compact, semi-compact or plastic, but if the member is slender, in that case you will omit the area in excess of the semi-compact limits. This area will be omitted above semi-compact limits, and the remaining area will be taken as the effective area. Okay. And epsilon here is 250 by Fi, square root 250 by Fi, that is the yield stress ratio. Now Euler's critical load, you know, that is FCR is equal to pi CR upon lambda square, and this should not be greater than Y. So with the help of this, you can plot a column strength curve like this. This you have seen in strength of material, so I am not going into detail. And this is the non-dimensional form of the column strength curve. But this Euler's column strength curve we will not use, because it does not account for the imperfections in column, that is any accidental eccentricity, etc., or initial crookedness. These are the various imperfections that can occur, or stress concentration, etc. So to account for this these imperfections, we have a different approach that is given by Perry-Robertson. This approach was adopted by IS code, IS 802/2007, based on which we have 4 types of column strength curves, that is curve A, B, C, D. Curve A are the perfect shapes with least imperfection. As the imperfection increases, we move towards curve D. So these are the various type of curves that was given by Perry-Robertson. When lambda bar is less than 0.2, your plastic yielding will occur, huh? No buckling will take place. Beyond this, you will have buckling. Okay. And these curves are plotted on the basis of this formula, you can see. This is how curve A, B, C are classified. So this is the formula that was used here. This will be FCD here. Okay. So on the basis of this formula, the column strength curve was plotted as per IS code. You can see this formula once. So FCD is equal to Fy by gamma MO upon phi plus square root of phi square plus lambda square, or it can be written as xi Fy by gamma MO. Gamma MO is 1.1 here. This will be not gamma MO, not lambda MO. Okay. Gamma MO is 1.1, phi is 0.5, 1 plus alpha, lambda bar minus 0.2 plus lambda bar square. Alpha is the imperfection factor that depends upon the curve. Curve A, lambda is 0.21, and as you move towards curve D, alpha will keep on increasing. Lambda bar is square root Fy by FCR. FCR is the Euler's buckling stress, that is pi square E by lambda square. Lambda is L E by R minimum. So using this, you can find out for the various lambda, you can find out FCD. Once you know FCD, you can do PD. And at different lambda, when we find the value of FCD, you will get this curve. You will simply get this curve on xi, okay. Or in the IS code, we have some charts also given based on that, and for every value of lambda, FCD is mentioned. Just you can interpolate from there. That will also work. That you have seen as well. Okay. So this was all about compression members. Okay. Now let's see some questions here. Then I will proceed further. Very simple topic. Huh? Very simple questions are asked from here. Let's see this question. Please try to do this question. Tell me the answer of this question. Then I will proceed further. Okay. Okay, do it fast. Let's start. The square root of the moment of inertia, that is by area, is my radius of gyration. This is only how radius of gyration is defined here. Okay, that is answer would be D here. D is the correct answer. If you are giving D me as the answer, it is very correct. Let's see the next question. Please tell me the answer of this one as well. Please tell me the answer of this question as well. Then I will proceed further again. Please tell me the answer of this question as well. Tell me fast, please. Tell me please, make it fast. Tell me answer. Obviously, Perry-Robertson approach is the approach taken by IS code. Okay, D was the correct answer. Attempt this question. This is also a very good question. No, not this one. Not this one. You will attempt another one. Not this one. Okay. So let's talk about built-up columns now. Built-up column, also known as latticed columns. Whenever we require any large cross section for which rolled section is not available, we can join two or more rolled section to get my built-up sections like this. Okay. So this is a section that is made by two channel section. So here the spacing is decided such that around both the axes my moment of inertia is same. You will get the maximum compressive strength out of that. So to ensure that both the column behave in unison, you use lattice elements. Lattice elements can either be lacing or it can be battens. You can see through the recommendations once. You can go through it once. Not important for GATE. If you want, you can go through it once. I have written everything here. You can just have a look through it. Not that important for GATE, I am telling you. Okay. This was all about the built-up columns. Please go through it once. Not a problem here. Okay. Then design forces, you should know of the lacing as well as batten. Go through it also once. Okay. Just go through it once. Not that important for GATE, I am telling you. Okay. You can go through it. Then we have column bases. The thickness of the column base formula you should understand. This is a column base. Here you have a column base. You directly don't keep the steel column on a concrete pedestal. You first make a column base so that the load is uniformly distributed. So the thickness of this column base, how you will design? Here the formula is given. So please remember this formula. This is my thickness formula, 2.5 W A square 0.3 B square F5 by gamma mo square root. Only one or two times question was asked, not that important. And T should not be less than the thickness of flange. TF here. Okay. Anyways. So this was all about column base. Now beams also I will show you once. So beam is a structural member that is subjected to bending action. Okay. In our course we have only beams that is subjected to only bending. Okay. This is a simply supported beam. A beam can be joist, that is a small section beam. These all joists rest on a girder like this. Okay. This is all about the beams. You can have the lintels as well. So, beam generally for a simply supported beam, one of the flange is in compression and one is in tension. So, to achieve economy, the moment of inertia about yy is less, whereas about zz is more. So, what happens is the compression flange have a tendency of buckling about this yy axis, but the tension flange will not allow it to buckle, due to which we can have a rotation also that will lead to a lateral torsional buckling like this. But in our course we will study only laterally restrained beams. You can laterally restrained beam by provision of cross beams or by embedding the beams, the compression flange into a concrete slab, or you can use this kind of bracing also. Class 1 to 3 I have already defined on the basis of local buckling. Class 1, that is a plastic section. The design compressive strength will be derived from the plastic moment plastic section modulus ZP. Semi compact section will be My, that is Ze by gamma mo, and slender section will be less than Ze by gamma mo. Okay. MD is a design moment capacity, Z is elastic section modulus, ZP is a plastic section modulus. That you already know, Z is ZP, how to calculate. I am not going into detail. For safety, your MD should always be greater than equal to Mu. Mu is the factored moment that is acting. Given that no shear buckling is taking place, that is d by Tw is less than 67 epsilon. If d by Tw is greater than 67 epsilon, we can have a shear buckling, that is a buckling in a diagonal direction like this. Okay. We only have rolled section in gate, so in our case d by Tw will always be less than 67 epsilon, so don't worry a lot. Now, to determine the bending strength of beam, we have two cases. One is the high shear case and low shear case. And when V is less than 0.6 Vd, we have low shear case. V greater than 0.6 Vd, we have high shear case here. So, this is the column strength, the interaction diagram between the bending moment and shear. This is on the basis of this formula. So, when V is less than equal to 0.6 Vd, in that case my MD is written as what? Let us see. This formula is missing here, I don't know why. Wait a minute. Okay. Let's see the formula once. Okay, this is my low shear case formula. That is MD will be directly beta B. So MD is directly, this is the low shear case. Okay. MD is equal to what? Beta B ZP Fy by gamma, and this should be less than equal to 1.2 Ze Fy by gamma, and should be less than equal to 1.5 Ze Fy by gamma for cantilever beam and for simply supported beam. Beta B is 1.0 for plastics and compact section. Beta B is the ratio of Ze by Zp, okay, for semi compact section, and Ze is for elastic section modulus and Zp is my plastic section modulus. Additional check is done to ensure that there is no excessive deflection at working loads. For slender section, we will take effective section modulus Ze by omitting the area that is in excess of the semi compact limits, that you already understand. Okay. Then we have the high shear case. For plastic and compact section, you can directly write like this. this is for m dv is equal to m dv is equal to md minus beta md minus mfd. This should be less than equal to 1.2 ZeFi by gamma mo, where mfd is the moment design, md is the design moment capacity as computed in for low shear case, whereas mfd is the design moment capacity by omitting this web area, by excluding this shear area or the web area. So, the plastic section modulus for this web area will be TWH square by 4. So, Fi by gamma mo Zp minus TWH square by 4 will give me mfd, and beta is equal to 2V by Vd. V is the factored shear force, whereas Vd is the design shear strength of the member. For semi compact section, you can directly write Md is equal to Ze Fi by gamma mo. Okay. For semi, that was for plastic and compact section. For shear strength, you can directly write that web area is existing shear for rolled section. Web, the shear area will include the flange as well due to monolithic casting, but not for the built up sections here. See here, this cover plates will not be counted in the shear area. Fi by root 3 gamma mo Av. Av is H into Tw here. It will be H into Tw here. This is Av here. HTW, here also HTW, but here it is because there will not be any shear flow because member is non-monolithic. Huh? Now we have various check for deflection, check for web buckling, check for web crippling. You can see here I have all written. Please go through it once. Not that important again. Design procedure I have shown. So this was all about beam. You can go through it once. Okay. Not that important. Just go through it once. Curtailment of plate also I have included here. Rest. Let's finish it off here today. So I am including everything in notes. You can just go through it once. And if you have any doubts, you can connect with us over the Telegram channel as well. My Telegram link I will show you all. My Telegram link, please go through the Telegram link here. Okay. These are our Telegram channels. Here you can stay connected with us. If you face any doubts, you can DM also. We will try to respond as soon as possible. Okay. Okay. This is our Telegram channel. You can just scan it and join out us there. Bye bye everybody. All the best.